Okay, in this chapter, I will introduce you the improper integral. Okay, uh, by definitions, we will have two kinds of improper integral. So, for the first one is the interval is infinity or the function has discontinuity. Okay, let me give you an idea. Okay, so let's see this curve that is 1 over x squared. Okay, the blue color here from 1 to t. Okay, we can see this area, the red color here, as area equal integration from 1 to t of 1 over x squared dx, and we can solve that easily. It's become 1 over x negative, and then we can plug in 1 and 2 and we get this expression 1 minus 1 over t. And if we are looking at these expressions, we know that the maximum number for this expression is 1. Okay, if you are plug in any real number of t. Okay, no matter how large t is, your a should be less than 1. Okay, the maximum is 1. So when you have limit as the t is increasing to infinity, you will get limit as t approaches infinity 1 over 1 minus 1 over t is equal 1. Okay, so when you plug in infinity to 1 over t, it's equal 0 in limit. Okay, so we can say that if we have the 1 over x squared, we integrate from 1 to infinity, it is equal to 1. Okay, now let's move to the official definitions. Okay, so if we have integration from a to t, a is any real number, we can write down the infinity as t, and we can use the limit as t approach infinity. So we will solve the integrations and then solve the limit. Okay, and the same thing when we have t to b. Okay, so when you have integrations negative infinity to b, b is any real number, so we can write down the limit as t approaching negative infinity of integration from t to b of fx dx. And all the limit, if it exists, we can say that the limit or the integrations is converged. Or if it doesn't exist, we say it's diverged. So it's convergent if limit exists, divergent if limit doesn't exist. Okay. And if both are convergent, we can define that if we have this integration from negative infinity until infinity of fx dx, if we want to separate this, both can be convergent and a can be any real number. Okay, now let's also look at the 1 over x. If we integrate 1 over x, it will become ln x. Okay, if you see here, this ln x. And if the infinity, we can use the limit, then we can solve the ln and then solve the limit. And when you solve the limit, it becomes divergent. So let's look at this area. The area for 1 over x, it has a large gap between the curve and the x-axis, right? And we say that because of this gap, it will have infinite area. Compare with the 1 over x squared, it has finite area because it's getting smaller and getting closer to the x-axis. You can try to imagine some number, like for example x is equal 10 or 100. If you have x squared, it will be multiplied twice, right? Multiplied by that number. So 10 become 100, 100 become 10,000. And here it's still 10, 100, 1,000. The number that can still be sufficient or still can be approachable, right? So that's the idea for 1 over x, it will be diverge. So we can also find some relations. Okay, so we can find if p in 1 over x with the power of p, if p is any real number, we can find the interval in which where the p is converged or where the p is diverged, or the integral is diverged. We can find the value of p. So we solve the x with power of negative p, we get these expressions, and then we solve this, and getting this 1 over 1 minus p and 1 over tp minus 1 and negative 1. So let's assume that if p is greater than 1, then as the t approaching infinity, this tp minus 1 also approaching infinity, and the conclusions 1 over tp minus 1 will be 0. And this is the conclusion. If p greater than 1, it will be converged. And you can use 1 over p minus 1 to calculate the area. If p is less than 1, so t1 minus p is going to infinity, and as the t approaches infinity, it will be diverged. Okay, I hope you get the idea. So you can make a conclusion that if you have 1 over x with the power of p from 1 to infinity, the integral will be converged if p is greater than 1, or diverge if p less or equal 1. Okay, that's the first type of the improper integral. The second type is discontinuity or discontinuous integrants. So suppose, okay, you see this curve, the function is continuous, positive, and it is having interval from a to b, but b is the asymptote. Okay, so we can solve that and make the a is equal to integration of a to some t, and we can make also using the limit, okay, as t is approaching b from the left. Okay, so we can make this approach to first calculate the integral, and then the second process will be the limit. Okay, now we have the discontinuity. Now the second one, now the first one is the from the left, p. Okay, the second one is a, so a is from the right, the vertical asymptote. So you can also do the same thing. Okay, so a b become t b. Okay, from t to b. Now if the integral converge, we can say it's exists, and doesn't exist, we say divergent. Okay, and if you have c, okay, discontinuity as c, and c is in between a and b. Okay, if you say the integral a to c and integral c to b both converge, then you can separate this integral become ac and cb. Okay, but if for example, in any type, when you have two elements like this, if one of them diverge, then all become diverge. Okay, but if this converge, you need to know the other one, whether it's converged or not. Then both are converged. Okay, then that's two type of the improper integral that interesting to be observed. Okay, I think I can show you the easy example. It's x and ln x cubed, and it's from e to infinity. You can start to solve this integration first. Okay, solve with the first substitutions. and you substitute become this one, and then easily it can be integrated, and then put in the integrands, and then you have the 0, and it's only half, and it's convergent. Okay. Second example, if you have this integral, I think the same idea for substitution, and then you have this. I'm skipping this part and going directly to this, and you can see if this expressions appears, then it will be divergent, because it's not a 1 over variables. Okay. And the last example for the integrations, improper integral, is this integral. Okay. First you need to see you have -1 and then 0, and see if you are plug in 0 or -1, one of them making the asymptote at least. Okay. So we need to make the limit as t approaching 0 from the left. We get this result if we are separating 1 over x and 1 over x squared, and we can substitute the 1 over x, and we get the tu is -1 over x squared. So we substitute with u and substitute also the integrands. Okay, become -1 and 1 over t. We solve it by integration by parts, and we get this expression. And because I want to erase this negative, I will switch the integrands, then it will be like this, and solve this limit later. So I will have the -2 over e, then a limit, and the whole thing here, 1 over t minus e power of 1 over t. And to solve this 1 over t, I need to approach with another variables. Let's say it's s. Okay. When t is approaching 0 from the left, s is approaching -infinity. If you are confused, let's see 1 over x. Okay, this is the 1 over x graph. This is st approaching 0 from the left. What will happen? It's going down, right? It's going down, and then we say that s is approaching -infinity. Okay, and we get this expressions, and a little bit trick for limit. Okay, I hope you still remember the limit. So e with the power of s, we can move here, and then it becomes -2 over e, and then limit, and then 1 over -e -s. So this is indeterminate form. And this is the L'Hopital rule I can use. And this become, if we plug in -infinity here, it will be negative, in which this is 0. So this is the answer, -2 over e converge. The last part, I'm explaining the one example in the class, but maybe later I will add more in the future if we have time. So suppose f and g are continuous functions. So f is greater than g greater than 0 for x greater than a. So if we have this integral, if this is converged, then the other integral that smaller than f, like say g, is also converged. But if g is diverged, then the bigger functions will be diverged. Okay? It's quite similar with the comparison limit comparison theorem, but it is applicable on integral. Okay, so I hope you get the idea. So if you have the fx, like blah 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 functions, you can think like g or h or any functions that you can think of. You can try this comparison and try whether your functions that, for example, you have f and you write gx, and you need to find whether if g is converged, then you need to prove that f is greater than g. If this is true, then f is converged also by comparison theorem. Okay, I think that's it, the review for improper integral. I hope you understand the basic idea that the integral can be solved using the concept of